Today we'll be looking at decision trees and how they identify common network issues like faulty network cables, AP or switch health, and wireless coverage. The algorithms used include simple random forest gradient boosting and XGBoost. Our example will be a simple decision tree algorithm. The essential steps in any machine learning project involve collecting data, training a model, then deploying that model. Decision trees are no different. Let's use a real-world example. In networking, decision trees can be applied to incomplete negotiation detection, MTU mismatch, among others. Our example today applies the fundamental problem of determining cable faults. A cable is neither 100% good nor bad, but somewhere in between. To isolate a fault, we can create a decision tree using features of a bad cable, such as frame errors and one-way traffic. We begin a decision tree by asking a question which will have the greatest impact on label separation. We use two metrics to determine that question: Gini impurity and information gain. Gini impurity, which is similar to entropy, determines how much uncertainty there is in a node, and information gain lets us calculate how much a question reduces that uncertainty. A decision tree is based on a dataset from known results. Each row is an example. The first two columns are features that describe the label in the final column, a good or bad cable. The dataset can be modified to add additional features, and the structure will remain the same. A decision tree starts with a single root node, which is given as a whole training set. The node will then ask a yes or no question about one of the features and split into two subsets of data, which is now the input of a child node. If the labels are still mixed, good and bad, then another yes or no question will be asked. The goal of a decision tree is to sort the labels until a high level of certainty is reached without overfitting a tree to the training data. Larger trees may be more accurate and tightly fit the training data, but once in production may be inaccurate in predicting real events. We use metrics to ask the best questions at each point, and so there are no more questions to ask. Then prune branches starting at the leaves to address overfitting the tree. This produces an accurate model with leaves illustrating the final prediction. Gini impurity is a metric that ranges from 0 to 1, where lower values indicate less uncertainty or mixing in a node. It gives us our chance of being incorrect. Let's look at a mail carrier as an example. In a town with only one person and one letter to deliver, the Gini impurity would be equal to 0, since there's no chance of being incorrect. However, if there are 10 people in the town with one letter for each, the impurity would be 0.9 because now there's a 1 in 10 chance of placing the randomly selected mail into the right mailbox. Information gain helps us find the question that reduces our uncertainty the most. It's just a number that tells us how much a question helps to unmix the labels that are known. We begin by calculating the uncertainty of our starting set. Impurity equals 0.48. Then for each question, we segment the data and calculate the uncertainty of the child nodes. We take a weighted average of their uncertainty because we care more about a large set with low uncertainty than a small set with high uncertainty. Then we subtract that from our starting uncertainty, and that's our information gain. As we continue, we'll keep track of the question with the most gain, and that will be the best one to ask at this node. Now we're ready to build the tree. We start at the root node of the tree, which is given the entire dataset. Then we need the best question to ask at this node. We find this by iterating over each of these values. We split the data and calculate the information gain for each one. As we go, we keep track of the question that produces the most gain. Found it. Once we find the most useful question to ask, we split the data using this question. We then add a child to this branch, and it uses a subset of data after the split. Again, we calculate the information gain to discover the best question for this data. Rinse and repeat until there are no further questions to ask, and this node becomes a leaf which provides the final prediction. We hope this gives you insight into the AI we've created. If you'd like to see more from a practical perspective, visit our solutions page on juniper.net.